This video is about making the coil for the electromagnet for the Toucan wood gear clock as designed and built according to Clayton Boyer's plans. The finished clock is a lovely unit. Being electromagnetically driven means that it's maintenance free and that it doesn't need to be wound or weights messed about with. It's a very robust system, quite easy to set up, works very well. The end product is lovely. This was built pretty much to plan. I did stiffen up the pendulum arm at the top to take out some of the wobble that tended to happen. The weight on the pendulum is a bit heavier than prescribed, but with this particular power supply, which is 9 volt DC output with a maximum 1 amp supply, works well, so that's good. It's connected to the clock via a plug. The only thing about that supply is the lead was a bit short. I had the problem with the coil, so I set up this test rig because my clock would only run for a day or two at the most before it stopped with a failed transistor. This meant the power was on constantly to the coil, which is a bit of a worry because although mine only got warm, a different supply may have caused it to get even hotter. It could have been a problem. So I set up this test rig, allowed me to test other components, transistors and what have you. I suspected inductive spiking. There was a diode on the original design on the drive coil to overcome inductive spiking, but I came to the conclusion that the problem was actually on the sensing coil and the sensitive base was being spiked. A diode was no use to sort this out, so I tried other transistors and came up with a medium power transistor, and I found a resistor on the base also helped enormously. To start the coil we need a core, so I had these 5-inch nails available. They're bigger than what most people normally use, I think, but no reason why it shouldn't work. The head ended up about 10mm diameter. The shank of the core is about 5mm, and I've got epoxy glued a 25mm disc of PCB board material. It's this fiberglass board with copper on one side. The copper's of no consequence in this situation, so it's just left there, but it doesn't do anything. It faces away from the coil and doesn't conduct with anything at all. The bottom plate's made of this hold type board, which has got copper strips on it. This stuff's sometimes called Vero board. This particular example is a bit thin, a bit flimsy, so I did actually find an alternative which is thicker, and this worked out to be ideal. So again, it's got the copper strips on one side, allowing components to be mounted on it. The strips can be broken at any point to break the track should they need to be, but in my case I didn't need to do that. Also with this you can use Vero pins, which are either a single sticking up through the board soldered to the track on the bottom, or you can even have a double version, so you can put components on both sides of a board. I only used the single ones here because that was all that was needed, and it works out quite well. Makes components very easy to change should they need be. This is the bottom plate with its 6 tracks leading vertically. I number them from 1 to 6, left to right. The blob of solder seen there is on track 2. That's where the start of the inner coil will be, as close to the core as we can get it, and the wire will be soldered on before we start any winding. That's just to make sure that the delicate wire is actually attached and we don't have a problem later because it'll be buried under the coil. This is the wire. It's 30 or 33 gauge depending on what system is used. It's also called 0.25mm wire if you measure it in metric. I use my wood lathe running in reverse, and because it's variable speed I could set a sensible pace of it. I made this wooden winding drum, the wooden winding drum has an exact circumference of 1 foot, about 305 millimeters, and it's designed that way so that every revolution is 1 foot of wire when it's wound on. As shown there, the power of the lathe is diminished to next to nothing by slackening the drive belt right off. That means that in the event the wire gets stuck, then the lathe will stop without breaking the wire. We have a counter which counts the revolutions of the measuring drum, and because the measuring drum is exactly 1 foot, every revolution is 1 foot of wire. So we need 200 feet of that, 200 turns, which will come out at 61 meters. So the drum, as I said, is 305 millimeter circumference, 97 millimeter diameter. So we set up for winding or measuring by zeroing the counter and starting the lathe with the wire attached to the drum, and it's just a matter of winding away till we get 200 feet. The spool's set up a convenient place to just give us the wire as it's wound onto the measuring drum, and the counter keeps us informed of how much wire we've got. So it doesn't take long to get 200 feet of wire onto this drum. It can now be taken out of the chuck and mounted at the other side, and the actual coil for the clock can be mounted in the chuck, and the first coil can be wound on. The core needs to be insulated from the coil wire, so this heat shrink is used. 28mm piece of it is shrunk onto the core, right up to the plate. The bottom plate will then eventually go hard against it. The bottom plate has the wire attached on track 2, close to the core, and the resistance checked. Here it can be seen on track 2, just about, and that's the starting point. The resistance of 200 feet of wire should be 22 ohms. For some reason my leads weren't up to the scratch and only showed 18, but it should read 22. So that's worth checking once it's wound on. Be one of the checks that we do once it's wound on. We also check that each coil is independent of the other coil and also not in communication with the core. So here we are mounting the assembly into the chuck. The bottom plate's only pushed on at this stage, hard up to the insulation on the core, the heat shrink. The jaws of the chuck will keep this plate in place as the winding happens. So I'll put this in the chuck hard up to the jaws. I haven't glued this at this stage because the glue will just get in the way and make the coil hard to rotate neatly. So I will just put a bit of glue on as I go along, and that will secure everything in place. So the winding carries on. It's just simply a matter of back and forth and wind it onto the core, the insulated core. The first 2 or 3 layers probably very neat. After that becomes more difficult to keep it really neat. Actually doesn't need to be absolutely perfect. As long as it's reasonable, it's okay, it'll work. So endeavour to do a decent job, but not essential to be absolutely perfect like a machine would have done it. It'll still do the same job. Having got the 200 feet on, we can insulate it with insulation tape from the outer core, and we can put the end through the base plate. That comes out on track 2 as close to the edge of the coil as possible, and the varnish can be scraped off the wire in the right place. So we've got bright wire for soldering. Again, it's important to do it now, so if there's a problem we don't end up with a shortfall on the wire, which is then buried under a load of other coil. That could also be tested at this stage to check that we've still got the 22 ohms. Once we've got the outer coil on, it's wound in the same direction, just on top of the insulated inner coil. The outer coil starts on track 6, finishes on track 5, the inner coil having started on track 2 and finished on track 3. One of the tests we can do is connect each coil in one at a time to a battery, and it should act as a quite strong electromagnet. As I said before, the coils can be checked that they're independent of one another and there's no connection with the core to either coil. So all that having been done, we've now got a working coil. Left connected to this battery, the coil does start to warm up after a short time. Left long enough it might get even hotter, but short term's no problem. So here we have the 4 ends of the coils connected, and this coil's ready to use. So we have start of the inner track, end of the inner track, start of the outer track, end of the outer track. This is the knife I use to scrape the varnish off the wire with. This is the transistor that's used in place of the low power one. It looks identical to it, does exactly the same job, and the layout is the same. So this is ZTX 451 transistor replacing the low power one that was originally specified. The performance of this transistor is more or less exactly the same as the original proposed one. So from when the flat side's facing us, we have the emitter on the left, the base in the middle, and the collector on the right. Well, when we're looking at the flat side, and that's how it mounts on the board. So it's ready for mounting on the board. Although it's not seen here, I did use Vero pins. Stuck Vero pins through and then eventually soldered the transistor to the pins. The transistor mounts on tracks 3 for the emitter, 4 for the base, and 5 for the collector. This 180 ohm resistor is what I used, and it goes between track 2 and track 4. As I said, that resistor improves the performance of the pendulum and protects the transistor. So they just get mounted on the board on the appropriate tracks. Obviously the cores will be trimmed later when the clock's being built. So this is the finished unit. The only thing that's required now is to connect the power leads, the negative and positive power supply. The negative power supply will go on track 3 and the positive supply on track 6. And that is the complete unit then, ready for the clock. I had a load of old power supplies, so I thought I might be able to utilise some of them, so I tested various ones. This is an old mobile phone charger. On the face of it, it puts out 10 volts, which looked alright, but actually it got very little current, so wasn't up to the job, so no good. Another one I tested with is this NiCad battery charger, allegedly putting out 10 volts DC. However, that was when it was under load. Without load, it put out more like 16 volts. It did work okay, it drove the clock, but it tended to overdrive it. So that would have involved reducing the power, so it wasn't worth messing about with. So having tested these power supplies and others, I eventually bought some power supply off the internet. This is a very cheap unit, does a good job though. It's a switching supply, has an output of 9 volts even with no load, and it can put out up to 1 amp and does the job quite well, so no problem with that. So the combination of this power supply with the transistor and the resistor has been all it's needed to do the job. So if you decide to build this, best of luck. I'm going to try and show some notes I made. I don't know if the camera will pick it up very well, but possibly by pausing the video you may be able to read it, but I'll also put it up as a graphic at the end, which hopefully will provide any information that isn't otherwise clear. So, as I said before, there's a possibility of overheating. These are the notes, and I hope if you decide to build this that you manage to do it successfully. Thanks for watching.